In this video, we're going to look at the acid-base properties of terminal alkynes. So this is going to be a type of reactivity that may be a little bit unexpected, or at least it would be for me. So the acid-base properties of terminal alkynes, and then we're going to look at a special application of the conjugate bases of terminal alkynes. All right, so let's first compare different hydrocarbons. Okay, so we have an alkane, right? An alkene, and an alkyne. Okay, and what we're going to do is we are going to look at the acidity of these. Now, we've already talked about before that usually hydrocarbons like methane or ethane are very non-acidic, right? But we're going to see that there's some differences in here. So let's go ahead and look at what would we usually look at? If we want to compare the acidities of these, what would we consider? All right, so what we would consider is this stability of the conjugate bases, right? So let's just draw out the conjugate bases. So we're going to take off one H, and we're going to be left with an anion. Okay, so plus H plus. So that's the acid-base reaction of ethane. All right, let's do the same thing for ethene. Plus H plus, and for ethyne or acetylene. Plus H plus. All right, so the most important thing here, like we've seen before in acid-base reactions, because this is an equilibrium, is the stability of the conjugate base. Okay, so what we want to know is out of these three, which is more stable. All right, what might we expect? All right, what's the difference? All right, we've got differences in number of pi electrons. What else do we have different? Okay, the other key thing that we have here is the difference in hybridization. Difference in hybridization. Right? And so if we look at these, what would be the hybridization of this anion up here, this carbon? All right, so this carbon has two pairs of electrons going to the hydrogens and another pair going to the carbon, and then it has this non-bonding pair here now. So it has four pairs of electrons around it. They all need some space. So this would be sp3 hybridized. This one is sp2 hybridized, and this is sp hybridized. All right, so how does different hybridization affect the stability of these different anions? Okay, so remember when we were talking about vinyl cations, we talked about the fact that if we have a sp2 hybridized or sp, the increasing amount of S character makes a carbon more electronegative. All right, so if we go down this direction, we have an increase of the percentage of S character in the bond, right? And so this essentially increases the electronegativity. All right? And so as we go down as well, since these are all anions, is an anion going to be more stable with a more or a less electronegative atom? Okay, we know that it'll be more stable with a more electronegative atom. And so it really, if we follow this, these anions should be more stable as we go down. Okay? The more stable conjugate base means that we have a stronger acid, right? So let's compare the pKa's then and see if we're right. Okay, remember when we looked at the pKa's of something like methane way back when we were talking about acid-base chemistry, we said it's super high. So the pKa of ethane is about like methane, is something on the order of 60. Okay? So remember what this means. If we had a pKa of 60, it would mean that the Ka, what would the Ka be? Would be 10 to the minus 60th. So the equilibrium constant would be 10 to the minus 60th. Remember, the equilibrium constant is products over reactants. And is this a big number or small number? So this is an exceedingly small number. So essentially, this equilibrium lies only over here. It doesn't go to the right at all. Okay? So now, from our prediction, if we go down to here, so this should become more stable than this one up here. So what should happen to the pKa? pKa should go down because this should be a stronger acid. And in fact, the pKa does go down. This pKa is around 40. Okay, so we're going down 20 pKa units, right? That's 20 orders of magnitude in the equilibrium constant. And if we continue to follow this trend, the pKa of an alkyne like this is about 25, right? So that's getting, so it's not so high, right? Still not super, this is alkyne, it's still not super acidic, but it's way more acidic than the other hydrocarbons. So let's see if we can fit it into all of these other acids down here. All right, so this is a little complicated. Let's just look at the different ones. What do we have here? We have water. Let's fill in some pKa's. Anybody remember? You remember what the pKa of water is? The pKa of water is 15.7. All right. Then what about HF? All right, you remember that from Gen Chem. So HF is kind of a weak acid as far as the other halogen acids. It has a pKa of about 4. The alkene, we can look up there, has a pKa of 40. What other ones do we know here? So the alkyne over here is 25. What about this acid here? Does anybody know what that one is? Okay, so this is acetic acid, and so its pKa is about 4.8. All right, then what do we have left? We have ammonia, and we have the ammonium ion. Which one of those two would be more acidic? Ammonium ion or ammonia? The ammonium ion is more acidic because if this is the acid, ammonia is actually its conjugate base. Okay, so ammonium ion has a pKa about 10, and ammonia is not very acidic either, so it has a pKa of about 36. So let's look at the relative orders here. What's the most acidic out of this group? We have HF is the most acidic, then acetic acid, right? What's next? Then the ammonium ion is next, then water, and what? Then the alkyne, then ammonia, and then the alkene. All right, so this alkyne now is getting a pKa down in the range that we've done acid-base chemistry before. Right? We already did some acid-base chemistry on ammonia when we did that dissolving metal reduction. All right, so can we actually remove a proton from that chemistry? So what do you think? If we add one of our standard strong bases, right? If we add hydroxide to a terminal alkyne, right? If we want to do this acid-base chemistry, this pulls off this proton, these electrons go back onto the carbon. We get the conjugate base of the alkyne. This is actually from acetylene. This is a generic term. It's called acetylide anion. All right, plus water. All right, so which direction do you think this equilibrium is going to lie? All right, so how do we figure that out? Do you remember? So remember, what we do is we look at the acids on each side of the reaction. We compare their pKa's. Right? So on the left side, what's the acid? So the acid is the alkyne. Remember, its pKa is about 25. Right? And what's the acid on the right side? The acid on the right side is going to be water. Its pKa 15.7. All right, so which direction is this equilibrium going to lie? All right, so water is the stronger acid, so the equilibrium would lie way back to the left. All right, so this is not going to work. All right, so hydroxide simply is just not as strong enough base. Hydroxide, not strong enough base. All right, so we needed to use a stronger base to do this. All right, so what we're going to do instead is we're going to use some chemistry we just saw. We're going to use NH2 minus. Okay, so nitrogen here has 2 bonds to hydrogens, has 2 non-bonding pairs. It gives a minus charge. This is called the amide anion. All right, so let's see what happens when we use that as a base. All right, so one of those pairs is going to react with the proton. Those electrons go back onto the carbon. We get our acetylide anion plus, what do we get here? We get ammonia. Okay, so let's do the same analysis that we did last time. So pKa of the alkyne is 25. And what was the pKa of ammonia? Okay, we did on the last slide. pKa is 36. All right, so which one is the stronger acid? So now the alkyne is the stronger acid, and so the equilibrium is going to lie to the right. All right, so we can do this acid-base chemistry. All we needed was a stronger base. Okay, so why are we doing this anyway? Okay, so the reason we're doing it is that this acetylide anion has an interesting reactivity in its own right. So we're going to have some practical application of this. Okay, so what can we do? So what we can do is that if we have an alkyl halide, okay, usually where this X could either be chlorine, bromine, or iodine, and we have our acetylide anion, what can happen is a reaction like this. So what happens is this pair of electrons reacts at the carbon, right? Why would it go to the carbon? Okay, it goes to the carbon because the halogen is more electronegative, and that leaves a delta plus on the carbon. So the minus of the acetylide anion gets attracted to the plus part of this carbon-halogen bond. All right, of course that carbon can't hold any more electrons. It has 2 hydrogens there too. So what happens is it gives up the halogen. Okay, so what we get is a bond between the 2 carbons, plus X minus. All right, so we have formed this bond right here. All right, so what's really cool about this is that we have formed a carbon-carbon bond, exclamation point, because in order to do synthesis in organic chemistry, right, because molecules are based upon carbon skeletons, we have to be able to make carbon-carbon bonds, and this is the first time we've been able to do this, all right? So this reaction, what type of a reaction is this, anyway? Okay, so this reaction is called a substitution reaction. Okay, we're going to learn a lot about substitution reactions in a couple of chapters. And it's also called an alkylation because we're adding an alkyl group. Okay? So let's see how we might use this. All right? So let's start with acetylene right here. And let's say we want to add some different groups onto that. We want to exchange those H's for alkyl groups. Okay, what we're going to do is we're going to go 1. We're going to add NH2 minus. All right, so we're going to use our strong base. It's going to form the acetylide anion, and then we're going to add some type of alkyl halide. Okay, so let's say we just use CH3 with a bromine, so bromomethane. Okay, the first step removes a proton, then we get a substitution reaction, and so we're going to get a methyl group attached to one end of acetylene. Okay, so then if we want to do it again, we can. So then we can do this a second time. NH2 minus, let's put a different group on there. Let's say, let's use iodo-propane. Okay, and I'm just choosing any kind of alkyl group and any of those 3 halogens. Okay, so I kind of arbitrarily are picking these. Okay, that was still there, and now we added 3 carbons onto there. So look at, in 2 steps from acetylene, we've synthesized 2, what is this, 1, 2, 3, 4, 5, 6, 2 hexyne. All right, and if we wanted to do more synthesis, then we know various reactions of alkynes that we could do, right? We could convert this to a ketone, we could add a halide, we could add 2 halogens, we could hydrogenate it to an alkene, and then we could do alkene chemistry that we've learned before. So this really opens up chemical synthesis, organic synthesis. All right, so there is one limitation that I haven't shown you here. So I already showed you what halogens we can use, but there's another one. So if I just use Rx instead of the way I have it drawn up there, so we saw what X can be. R has some limitations as well. So it can either be a methyl or it can be primary. Okay? If it's secondary or tertiary, then there's some competing reactions that take place that don't allow this to work, and I'll tell you about those in a couple of chapters. Alright, so in the next video, what we're going to do is we're going to look at some different examples of how we can use these reactions in chemical synthesis.